Started. So good afternoon, everyone. Maybe some of you, some of it's good morning, but it doesn't look like it. So what we're going to do today is I'm going to present a stakeholder webinar, which is maybe slightly different from the typical science presentations where you get results at the end of a project. This is more sort of a mid-project progress report that provides you with an opportunity to give us input, because I think many of you have been in this frustrating situation where, scientists present results and say, and then you sit there and say, I wish you had thought about this, or I wish you thought about that. So this is really designed to provide sort of the community with an ability to provide some input on this ongoing project. So my name is Martin Wiedmann. I'm the Gallard Family Professor of Food Safety here at Cornell. And what I'm going to talk about today is a project that focuses on multiple projects that focus on the development of data-informed approaches to reducing food waste. We'll mainly talk about dairy, but importantly, we see dairy as a model system. A lot of the work we do here is very easily applicable and is being applied to other systems, including produce. And every now and then, I'm going to throw a mention of that work in. I'm going to talk a little bit about the specific project that this webinar is about, and then start with some background and then really dig into the meat of the project. So the main project I'm talking about today is supported by the Foundation for Food and Agricultural Research. FAR requires matching funds. The matching funds have been provided by a number of organizations and groups, including the New York State Dairy Promotion Board and Chobani. And the actual title of the specific project is a lot more buzzwordy, and it's reducing food waste by reshaping consumer behavior using data-informed dynamic economic incentives. And at the end of this, I hope you have a better idea of what we mean with these buzzwords. These are the Cornell faculty involved, and so you can see we have a diverse set of expertise from the more classical food science to Aaron Adalja from the hotel school, who comes with more of an economics background, to Renata Ivanek from the College of Veterinary Medicine here is really a modeler. And so if you have any specific questions, input after this, you should feel free also to reach out to any of these individuals. And their contributions to this will become a little bit more clear as we go through these presentations, do this presentation today. A number of them are also here, so you can direct questions directly to them if you want to. This project also have an advisory council that meets about every 6 months. They are listed here, so represent a broad group of people that would be users of some of the products we develop, or could provide input on how to make some of these products into a point where they could be commercialized. So the big picture and the long-term goals of this project and some similar associated projects is to develop digital food systems, and we'll call those digital twins, and we'll introduce that term later, that can be used to make better food safety, food quality, and overall processing decisions. So to develop decision support systems. As I said, we use fluid milk as a model system, and there are two key parts of what we're doing here, what I'm going to present. First of all is to develop these decision support tools and associated intervention technologies, but we're really going to focus about the decision support tools here today. And part of these decision support tools and these predictive models can also be used to dynamically predict product shelf life and pricing. So two key concepts: decision support tools and dynamic shelf life prediction and pricing. Let's talk about predictive models or decision support tools first. Predictive models that we develop, and very simplistically answer the question, or designed to answer the question, what is the expected number of consumers that are exposed to a spoiled product under the current conditions? That means current processing, current contamination of raw milk, current distribution chains, temperature distributions, etc. What we're doing here is not your grandmother's shelf life stuff, where you inoculate product or take product that comes off a line and set it in an incubator at whatever your favorite temperature is, 40, 42, 45 Fahrenheit, and then taste it at shelf life date or shelf life +5 and see whether that still tastes well. These are Monte Carlo simulations that take into account the variability we experience throughout the chain. And one key one is obviously the temperature conditions the product is exposed. With these models, we can use them and design them to help people in industry make decisions. And this happens through what I will introduce to sort of what if scenarios. And I look at them as what happens if. What happens if I reduce initial contamination of my raw milk by X? How much can I increase the shelf life? How much can I extend the date that I put on that package to maintain the same consumer complaint rate? And this can be used to make the best decisions and investments, because often, companies may decide between technology A and B, say which of these should we implement, and sometimes one is more expensive than the other, or might incur different types of expenses, capital investment versus sort of continuous cost of running it. And then the question is, what does that do to my shelf life? Or what's our best estimate? And the typical classical shelf life studies are not necessarily going to make the best decisions. Sometimes you can't really do them because you don't have the equipment in your facility yet, because you haven't shelled over the $2 million yet to put this equipment into your facility. So these tools help make better decisions. And we'll get more into the details of that. The second one is the idea of dynamically predicting product shelf life and price. This is not, a new concept. I mean, we've all seen this, maybe not so frequently with milk, but milk gets closer to end of shelf life and we discount it. It costs less. And one could think of this as a not very dynamic, but somewhat of a precursor to dynamic pricing. And we're all familiar with dynamic pricing, obviously, when we buy airline tickets, where the price changes depending on demand and availability of seats on different routes. The way we see this working is that if you have your classical fluid milk container, you have a time temperature indicator that sort of gives you some indication of the temperature history of that container. You have a QR code that provides you with an ability to link this milk to maybe the production lot, the raw milk that went into it. You could run a model that predicts the shelf life. And if this system also links into your supply, like how many cartons of milk are left in grocery store A, it will predict the price for you. And that will, with regard to spoilage or food waste, this will help move product that gets closer to shelf life, end of shelf life, by reducing the price. That's at least the conceptual idea on this. So, two concepts. One of them is dynamic labeling, and the other one is decision support tools that we're going to touch on a couple times, or multiple times today. All right. So the specific project has three objectives. Number one is to develop these prediction tools. Number two is to design and implement interventions to see how we can reduce food waste. And to objective three is to really implement them in the real world. So those are the three ones today. We focus on one because that's where I've done most of the work, but I'm happy to entertain, we're happy to entertain input and ideas on objective 2 and 3. I'll touch on them a little bit, what we've done there and what our plans are there, but not as much detail as objective 1. So let's talk a little bit about food waste and loss as an introduction. I think we're all sort of roughly aware of the impact of this, right? It's a major problem. Lots of food in the US is reported to go to waste. And there's some estimates suggest that a considerable portion of this is actually microbial growth, so microbial spoilage. Two big ticket items for this are fresh produce loss and fresh fluid milk loss. These are substantial, and obviously reducing the volume of produce and fluid milk wasted at production, processing, retail, and throughout the chain represents a significant opportunity. I never really, these numbers, 40%, 13.9 billion, I always take them very much with a grain of salt. There's probably a wide uncertainty around these values that, most of the current estimates really don't report, but they should, and they will in the future. It's just, give you an idea of sort of billion pounds lost due to different products, and dairy and vegetables, big part of this, which are the two major products we're really focusing on. Dairy, through this currently funded project, but then we also have some ongoing work funded through a couple of different avenues on produce waste and spoilage, applying very similar principles to what we do, what I'll talk to you about today with regard to milk. One thing I want to just quickly mention, and I've been guilty of this, I've been throwing around food loss and food waste sort of interchangeably. These are actually different, and they depend on where in the supply chain you look at. So food loss would be anything that happens outside retail, food service, and consumer. So that's on the farm, in the processing plant, etc. That would be considered food loss. Food waste is then everything that happens retail, food service, and consumer. So you don't finish your plate at your favorite fast food restaurant, that food gets tossed out, food waste. You don't manage your refrigerator well at home and you have to throw out half the food you buy, food waste. We plant 120% of what we can harvest at the farm, and some of it we plow under because we just don't need it. That's food loss. This is important to consider because sometimes the numbers get confusing. It's like, man, you just talked about 40%. Here in this chart, everything looks like 10 to 15%. How can that be? Well, this one is food loss, not food loss and food waste. So just something to keep in mind. All right, let's talk about prediction tools for food spoilage. So this is sort of the major emphasis of this project that we've worked on so far. So we picked fluid milk, so not all dairy products, but a specific dairy product as a model system. Partially a big part of because it's an important product that spoils, substantial impact, but part of it also because we have a long-standing program at Cornell that's called the Voluntary Shelf Life Project. And this is a project that monitors fluid milk quality and has monitored fluid milk quality in essentially all New York State fluid milk processing plants over 40, 50 years. If you've gone to the state fair, the New York State Fair actually gives out prizes for the best fluid milk in the state. That's based on these data. So we had data, and that's what every modeler wants is data. So we had those, which made fluid milk a good model system to just figure out how we can develop these decision support tools. A little bit on the basics of food spoilage, because you need to know the biology to do these models. If we very simplistically look at spoilage of fluid milk, it can happen by two different routes. One of them that's called post-processing contamination. So these are microbes that are introduced after pasteurization, after the processing part. And these would be often Pseudomonas species. These might be coliforms that can grow at low temperatures, might be some non-coliform Enterobacteriaceae. These are typically different types of gram-negative organisms. The other major mechanism of microbial spoilage would be due to spores. These, and more specifically, endospores. So these are bacterial spores that are present in the raw milk. Typically, they can survive heat treatment. They can survive your high temperature, short-time pasteurization. And then some of them will start growing in the milk, even if it's stored at refrigeration temperature. The poster child for spore formers that does this is Bacillus stephanensis. And why would I not mention it? There's a nice name after a German city close to my home in Munich. And cyclotolerant Penibacillus species. Those are the two big ones. So when we model shelf life and we want to develop these decision support tools, when we want to develop these tools for dynamic shelf life prediction and pricing, we need to account for both of them. I'm going to first just give you an overall idea of how these simulations will work based on the work we've done on spore formers, so one arm of these two parts of spoilage. And we're then going to go into what we've done for post-pasteurization contamination. And Al, I see something shows up in chat. If you feel like, not going to read it, but if you feel like it's something I should answer now, just interrupt me at any time. So if you can monitor the chat, just chime in and interrupt me. Because some questions I feel are just going to be better answered during the presentation rather than at the end. Right. So back to this. So Monte Carlo simulations to predict spoilage due to spore formers. So Again, we're not going to get deeply into technical details, but the idea is that we have some major inputs for these models. One of them is how many spores do we have in a raw milk? And this is not one value, but it's a distribution, right? Some milk has higher loads of spores. So this is on the x-axis, we have this in a log scale. So 10 to the 1 will be 10 per mil, 10 spores per mil, and then you go very low to 10 to the minus 2 to higher. So you have a distribution for that. You have different categories of subtypes, different organisms. So we gave them numerical designations, allelic types, but different types will also represent different species. Bacillus stephanensis versus Paenibacillus peoria, for example. We then have experimentally determined how quickly and different organisms grow and their overall growth parameters between lag phase, maximum growth rate, and what's called Nmax, or the maximum number of bacteria. And you can see different subtypes will have different growth rates. And then we run a Monte Carlo simulation, which basically we pick from this distribution, say, container number 1 has, picked based on the distribution, let's say, 10 to the 0 spores, so 1 spore per mil. Based on the distribution here is a subtype 3. Here's how fast it grows. Here's what we get. So initial count, subtype, final concentration. Next iteration, initial count, subtype, final concentration, and so on. So we will go through these different categories, and the final count is per mil is at day 14 in this case, but we can set it for different days. So this is the basic idea of Monte Carlo simulations. So what does it give us? It gives us sort of percentage values. And so we can look at a baseline model where we can say, day 21, milk was the average, fluid milk made was the average supply that on raw milk that you get in New York. In this case, we set the storage at a single temperature, not a distribution. But the models now will incorporate distribution because milk is not stored at 1 temperature. Some milk might be stored at 2 degrees for most of its shelf life. Other one might be 2 degrees centigrade. Some of it might be stored at 5 or 6 degrees centigrade, so more like 44, 45 degrees Fahrenheit. So we can say the percent of half gallon, so that's the common size, that is less than 20,000 CFU per mil, which is a regulatory cutoff, is 25%. So 25% of very low bacterial counts at day 21, but if you move at day 24, it's 5.1%. So that's our baseline based on what's currently happening. Once we have this baseline, we can then assess what happens if we would make certain changes to the supply system. We can also, somehow this is not, we can also make histograms, and we can even make some little movies, which this one is, which it shows the distributions of bacterial counts over shelf life. So you can see at the beginning, you have more half-gallon containers have low numbers, and then more and more have high numbers. So that's what we call our base model. We compare this to our historical data, say, yeah, this is about what's really happening. So this model gives us realistic data. We can then take the baseline scenarios and say, what happens if you make changes? What happens if we change the distribution? We reduce storage temperature by 4 degrees. We go now from 34% less than 20,000 to 91% less than 20,000. So much larger proportion of all containers have low bacterial numbers if we reduce storage temperatures from what's equivalent to probably a 44 Fahrenheit to about a 39 to 40 Fahrenheit, which is very well established and is like sort of a doozy to a certain extent. Yeah, we all know that, more or less. We didn't have the numbers as nicely as we do, but conceptually. But once we have this, we can again develop the movies, but then we can move into more interesting truly decision support type scenarios. So for example, we can say, what if we use microfiltration on the milk? What will that do to our bacterial counts over time? What will it do to our shelf life? Yeah, that's where it is really a worthwhile decision support tool, because investment into microfiltration, bacterification, and other technologies is expensive, and one would want to be able to assess the impact of changes, expensive infrastructure or equipment investment into shelf life. And we can predict that with microfiltration, we can extend milk shelf life by 4 days. And we can then just summarize this here. We can use different types of parameters. So you have initial condition, we lower refrigeration temperature, we reduce raw milk contamination level with spore formers by 2.2 logs, about a little bit more than 100-fold through microfiltration. And then we can look at average bacterial concentration at day 21, fraction of containers that exceeds a certain threshold, and we can then calculate out what that really means in terms of shelf life extension. So this is the basic tool set that we put together. Now, this was for spore formers. One graduate student supported on this project has developed essentially a very similar model now for post-pasteurization contamination. So now we can model both branches of the spoilage, because we have both models, and we're now in the process of combining them into a single easy-to-use model. The second model, and you will see, is very, very similar. We have Monte Carlo Simulation Model. We run what-if scenarios, and the what-if scenarios could be what happens if we reduce the frequency of contaminated samples due to post-pasteurization contamination. That often may mean improved sanitation, replacing equipment with more easily sanitizable equipment. Some of them can be expensive infrastructure improvements, to improving storage and temperature control, to eliminating specific problematic subtypes through a strategy that one could call seek and destroy, where we're actually trying to find the specific source of post-pasteurization contamination of, let's say, an organism that grows very fast at low temperature. So different scenarios, when we combine it, we can now help companies make decisions. Do we focus on controlling spore formers, or focus on reducing post-pasteurization contamination? Which strategies are we going to use in order to extend the shelf life of our product? And that then leads us to having these models that can dynamically predict shelf life, taking everything into account, and that could run behind the scenes for not just the decision support tools, but also for the dynamic pricing applications. And we're working on something similar for produce, just to give you an idea. So if you're interested in something else, in applications other than fluid milk or other than dairy, we are working on that too. The basics are very, very similar. The details in terms of types of organisms, et cetera, are obviously different. So I'm going to finish up with one other model to show you, give you another estimate of how these models could be used by industry for decision making. One of them, a set of models we developed, one of them is collaborators, is on estimating consumer exposure to a spoiled yogurt, where we focus on mold and yeast and mold contamination. And processes have an ability to use different intervention strategies, all natural versus, the classical preservatives that are not a clean label, et cetera. So people try to make decisions: which one should we use? How does it impact our shelf life? So here we developed a model that looks, again, from production to consumption. Very, very similar. I'm not going to go into the details, but we're looking at the time to visible growth for one organism. And it helps you basically predict how long does it take, and what proportion of your yogurt cups will show up with mold. You can use it as percent of cups. We can, in this case, express it as saying, under certain assumptions, and these will be specific for each facility, how many consumers will experience visible mold growth out of 1 million cups. And the beauty with this is, if you have consumer complaint data, which all of you will have if you're in this business, you can then align this with your consumer complaint data, right? And you can have some estimates that maybe 1 out of 20 consumers will actually call or file a consumer complaint. So you can say, yeah, this number makes sense with our consumer complaint rates. And you can then assess what different types of interventions would likely do to your consumer complaint rates. We can use these models again to run different what-if scenarios, whatever someone's heart really desires, as long as we build the model right, to help companies make decisions. And if you want to read more about those, these are 2 papers that we published on these sorts of models. So with this, I hope I've given you sort of an idea of what's possible and the type of work we're doing with modeling and with developing these decision support tools and these modeling tools that can be used for dynamic pricing. So the next part I'm going to go into, and this is a little bit shorter, is how we're going to really work on objectives 2 and 3 of this grant, which is prevention of spoilage and then implementation of interventions. So the prevention part, the prevention part of this for this specific project is really focusing on right now on 3 different approaches. One of them is the impact of raw milk quality improvements, including sort of the economics of this. What premiums do we pay for farmers for improved raw milk? Can we increase shelf life, reduce spoilage to that? The second one is reducing post-pasteurization contamination through, sorry about the typo here, antimicrobial coatings. This is a project run by Julie Goddard and her team. And then we're looking at spore removal technologies. We already talked a little bit about microfiltration. Bactification will be another technology. So we're developing a lot of the input data here that can help us with developing these models, but also have started using the models to run what-if scenarios that will help us determine which of these interventions might be most valuable. So that's one arm of the prevention part. It's really, either developing new technologies or implementing them at scale to see how well they work. Another challenge that we sort of predicted and we're running into it is obviously, how do you define what the best intervention and control strategy is? Because intuitively, for all of us, it's probably very clear that this is not a one-size-fits-all. Depending on what raw milk supply you have, and more general, what raw material supply chain you have, what's the size of your processing facility? Are you making product, for example, with certain preservatives? So not a lot of different things. The optimum will differ. The optimum method will, for reducing spoilage and for increasing shelf life, will differ. So Renata's team, it was a postdoc that has now moved on to a faculty position, really developed some optimization models that really take into account economics. We approached this with 2, and Renata and her group approached this with 2 different sort of models. One of them is to impose a budgetary constraint, basically saying, hey, you got this much money to increase shelf life. Which method is best for the type of product you make? The second model is, what's the minimum budget? How can I get a certain extension of shelf life, let's say an extra 3 days, an extra 4 days, with the least amount of money? Now, it's probably pretty clear to all of you in the real world that, these models, we can develop them, but we need real world data from a processor to really help company X or Y to make these decisions. We've used these models with some semi-hypothetical scenarios of different size processors with different quality of raw milk, different production volumes, and not surprisingly, the combinations of interventions that provide you with the optimum result will differ depending on those differences. But what that means is we have some tools available that if someone is really interested in taking this to the next step, we would love to work with you to see how we can apply this to a real facility. So, whether you're from industry, you're interested in working with us on this, whether you're from an academic partner institution, another university, say, hey, if you have a facility that might be interested in that, we definitely would love to have some collaborators to expand this and like to see your input on how to make these things more valuable. Another interesting thing we ran into it, and this is some work that Aaron Adalja and his team are doing, is really that sort of question like, well, what is the value of extended shelf life, right? And we've asked a lot of people in the industry that, and it's like, okay, so we extend the shelf life of your half-gallon container of milk for 3 days. How much is that worth it to you? Is it worth like a penny, a quarter? And Aaron and his team, and specifically Paulina, have worked on a willing consumer studies, conjoint analysis, to start to estimate the willingness to pay. And I'm just going to highlight one result. And what this study found, it's an estimate about 7 to 8 cents per half-gallon container for an extra day of shelf life. Now, this is one study. This is not the end-all be-all, but with a couple of different approaches, we come into a similar value, maybe slightly lower. So most of our estimates go into sort of 4 to 8 cent range. So again, we've developed some of the methodologies that could be applied to other products now to help people estimate the value of additional shelf life. Now, once again, that will differ from facility, company to company. If you have a major contract that they'll only buy from you for an extra 4 days of shelf life, the value of those 4 days might be higher. In other circumstances, the value might be lower. But we have some approaches to assess that. All of this combined will obviously help us assess what interventions do we implement when and where. And we have that economic part to this equation. So I want to finish up is really what are our long-term goals? Where are we going with this? And I'm going to come back to a term that I sort of mentioned before, which is the idea of a digital twin. And that idea was really, or that concept has really been termed sort of more in the medical field. And the idea there, as far as I see it, is that a digital twin would essentially be a model of an individual person, let's say Martin here, that takes into account my metabolism based on my data, my liver function, my weight, and so on, and could be used before treatment decisions are made. My genetics, treatment decision are made. What will happen if we treat Martin's diabetes, which I don't have, but if I had it, with drug A or B or C, how quickly will it metabolize? What's the optimal concentration? Because maybe my liver function is limited and therefore the drug doesn't get metabolized as fast. Maybe it gets metabolized more rapidly because of my genetics, et cetera, et cetera. So we can use this to really individualize treatment from person to person. Our goal is to develop similar digital twins for food systems, everything from primary production to the consumer, where we can then use that to say, what happens if we do X, Y, or C in the farm in terms of new technologies, maybe change the type of bedding the cows are on, maybe change how we clean and sanitize. What happens if we make certain changes in the distribution chain? Maybe just take the temperature down by 2 or 3 degrees. What does that do? And we can look through the chain and really run these systems-wide what-if scenarios. What I've shown you here today is bits and pieces that I think we can start to piece together to build sort of a more complete digital twin. I'm going to illustrate this now more in our food safety work, where we've really have models for everything from how likely is produce to become contaminated with pathogen in different fields based on GIS tools. And just for those of you worried about it, this is a Cornell field. It does not disclose any risk factors for a commercial field. To refining these models, to talking about factors that impact likelihood of foodborne pathogen contamination in the water that is used to irrigate produce or otherwise is used in produce production, to looking at transmission in processing plants through agent-based models, where we now in a much higher, more detailed level can actually model post-pasteurization contamination. And you use that with these models that really show what happens in a processing facility over time. where we can then start to see, we can actually model people coming in and out, water coming in and out. And if you look carefully, you see some of these yellow dots show up that are listeria, and we can model how they move into a plant, and we can find out what happens if we make certain changes. Maybe if we separate the two lines, maybe if we sanitize more frequently, maybe if we close off a door, and we can run those what if scenarios. But we can now put all of these types of models together to start to developing something that more resembles a true digital twin. Ultimately, we can then use our past data to use some of the more modern tools of whether it's random forest analysis or more broadly machine learning to identify risk factors and then even better predict the likelihood of post-pasteurization contamination. And if you want to see how that works, check out a paper that Sarah just published in Journal of Food Protection, where we can use machine learning to really improve data analysis, decision making, and potentially use some of that inputs for some of these digital twin type models. So in summary, I hope I've really sort of impressed on you the sort of the range of decision support tools that are being developed. And I really probably just hit the sort of tip of the iceberg. But I think making a decent breadth of introduction to the tools we have for reducing microbial spoilage. I think you've seen that the same tools can be used for food safety issues if that's what you're interested in. I think the idea of digital twins are the future. Not the idea, but digital twins itself. My expectation, hope is that any new food processing facility that is built going forward, we will build the facility and at the same time in silico on a computer, build a digital twin of that same facility where we can model out everything from movement of people to movement of bacteria to movement of product to optimize these facilities. This goes way beyond food spoilage. I think I've given you a glimpse into sort of the challenges of the economics of this. Sort of what is added shelf life versus not straightforward. And I've just been looking, and we've just been looking at in terms of the impact and importance for a facility. If we start to look into sustainability, what does extended shelf life do for sustainability? And what sustainability metrics do we use? It becomes even more challenging, but we're sort of nibbling away on these problems, I would say. So with that, I want to acknowledge the collaborators on this project, the students and staff that have really been moving this along, and the funding sources. As I said, it was mainly funded by FAR with matching funds from Giovanni and the New York State Dairy Promotion Board, and then the Walmart Foundation, as well as the Cornell Institute for Digital Agriculture, supporting some of our produce spoilage work. So with that, I'm going to open it up for questions, inputs. So this is one where, it doesn't have to be a question. You can actually make comments. You don't have to sort of make it a fake question when you want to just comment on something. So, okay, maybe so people can just unmute themselves or can type things into chat. And I'm going to look at some of these questions. Okay. Enrico asked, what's your definition of a digital twin? Let me know if that was not clear. I mentioned it early on, but then I went into it. So if you want some more explanations, let me know. Jean asked about slides being available. Yes, we will make those slides available. I may have to check with some of my collaborators, to be perfectly honest, put these together somewhat last minute. So I just want to make sure there's nothing that some of our collaborators don't want to see. But you get some version. You might take out a graph or two there, but it shouldn't be an issue. Okay. Any questions, comments? Anyone else from the team wants to add something to it, feel free to.
Hey, Martin, Alejandro here with Giovanni. That was great, thank you. One of the things I think sometimes is, once you know the initial numbers of potential spoilage, spores, or something going forward, then the rest seems to be very, very well thought on that. But I think that would be always the hardest the hardest step of all, because if you're producing and you do a sampling plan, you're never going to predict what's in each bottle or cup or package. So there would be a lot of variability there on what goes in to each package. And then to put something based on time temperatures or any other things, you may sometimes probably destroy more instead of less, because you may believe that is, well, based on the average or something, and it actually has less in that run or that load or that thing. So I think the problem goes back to also always understand, how do I sample in my plant, and how can I predict the levels that could be, because it varies all the time. Mm-hmm. So that would be my thinking on the model. Mm-hmm.
Yeah, you bring up a really, really good point. And it's essentially the question, like, how do you get the right and enough input data to make this stuff work? You know, this sounds great, but
yeah,
you know, I don't have time to do a 50-year study of a supply chain to build a model that then may be able to predict stuff, right? And I want to divvy it out a little bit. So it depends on the specific types of spoilage issues. I think if you look at something like spore counts, getting a distribution of the frequency is tedious, but it's doable, and we can do it, because essentially, yeah, every fluid milk will have spores, bacterial spores in it, and we can come up with that distribution. The problem then is what I'm going to call the granularity. So how much details do we have? Because often it's not enough to know we have on a mean of 1 spore per mil, and this is the variation around it. But then it also gets a question about, well, is that spore an organism? And you sort of pointed it out. Is that spore one that, how likely is that spore to survive HTST or not? And what's the log reduction we get? And that will differ depending on the organism. How fast will it grow? Will it grow at all? That will differ from organism to organism. So having those data now, what's the distribution of spore numbers for all 50 different spore formers becomes, you know, not impossible, but practically not executable. Now, let's take something else that it's really, really difficult, would be something that's a lot more sporadic. So let's take, for argument's sake, mold contamination that, you know, might happen, or anything that might happen 1 in 1,000 containers or 1 in 10,000 containers. How do you get an estimate? It's whether it's 1 in 1,000 or 1 in 10,000, and how much does it vary from day to day or from season to season, et cetera. And those numbers, obviously, the sampling you would have to do is massive, and even then, you know, you don't know how it changes over time. So you're really going to often have to go back to essentially expert opinion, and then try to come up with a way to validate that you're in the right ballpark. And I think consumer complaints is one way to do it. So we can develop these models and say, okay, we developed a model with all the best data we got, and it predicted that, you know, out of the Cornell strawberry yogurt, you know, half of them will have mold by the time the consumers eat it. But we only get 1 consumer complaint per 100,000 packages. Okay, that model isn't working right. But then you can adjust it to hit the observed level. Now that might sound a little bit sort of first of all, scientifically not super valid, because you just like sort of back adjusted to give you the results you want. But if you look at classical risk assessments, that's still routinely done because it's needed. So if you look at the Listeria risk assessment that used mouse model data, yeah, it predicted that hundreds of thousands of people would die of listeriosis every year. I mean, like, you know, that's really not happening. So we're just going to adjust that model because we know it's about 1,600 cases a year to predict that right number. And, you know, and I have to put in, you know, every model is wrong, but some of them are useful, and you make it useful by adjusting it. So I think that's where, you know, should I call it science, or I think experience and industry work in this academics really comes in to say, how can we develop models that are useful, even in the absence of some of these fine granular data? And really, our experience has been, it usually is doable. And then if the model is wrong, well, it's always wrong. If the model predictions are not useful, then we're just going to have to improve the model over time, and we tend to get there. So but I think it's one of the reasons why industry isn't really jumping on it. It's like just too many data needed. But I don't think it's as bad as we think it is. I don't know if anyone else wants to jump in, or Alejandro, if you have some retort to that.
One thing to add that I think is interesting, not to think about spoilage, but when you do your equations and that based on time and temperature, I mean, one of the key things that we look at is that temperature abuse actually, while it makes the product safer, no, it lets the lactic acid bacteria to grow more, producing more lactic acid. So let's say if I have a strawberry on the bottom, the lactic acid will affect the color of the strawberry, which is not good. But if I have a key lime, it doesn't really have any effect because the acidity doesn't really add anything. So it is interesting not to look at it. It will be interesting to see this not from a spoilage situation, but from a lactic acid bacteria increase in load that could create a little more lactic acids, reduce the pH, that affects the quality of my product. And that's what I always try to set my shelf life based on that.
Yeah, this is actually a really good point you bring up. So, and I think we rightfully every now and then get hit by we're too much focused on just microbial food spoilage and sort of ignoring the non-microbial ones. And I'm not sure that everyone completely follows. So the issue is, so in general, you would think, hey, if we store a food product at abusive temperatures, let's say at 50 degrees Fahrenheit, so that's going to be bad. The product's going to spoil sooner. And microbial spoilage, but with some fermented product, that might simply mean the lactic acid bacteria grow faster, and therefore actually your pathogens or your spoilage organisms are less likely to grow because the product becomes more acidic. But that acidity then can affect other compounds, such as Alejandro pointed out, the strawberries or the color development, or just the overall taste, because now the product tastes more acidic. And that so I think to add these sort of chemical non-microbial spoilage issues, and it's something that I need to always force myself, and thank you for reminding me of this with this comment, Alejandro. So I think that's an important one to not forget about. Some of these sort of called unintended consequences, but also the things that might not, where changes will also affect non-microbial spoilage and consumer acceptability, I'm going to call it.
I'm just wondering, this is Phyllis Posey from Posey Global. I'm just wondering if you see yourself, as you develop the digital twin concept, do you see yourself creating some kind of protocol or useful guidance for benchmarking and the kind of sampling that Alexandra was talking about, in terms of as a methodology to make all of this more useful to industry and to folks who are looking to do the what ifs?
Yeah, so that's, I think it's a really good question. And Renata, if you're still on, maybe you want to jump in. I'm going to give it a first shot. I mean, part of it is through the papers and the stuff we do, it definitely says what are sort of the data needs. And there's sort of a guide to it. And the way I look at it, again, I'm not the modeler, very simplistically, is we build a model with the data we have. Where we don't have data, we fill it in with expert opinion, which is exactly what it sounds like. We could ask 3 experts and think, hey, what do you think? How often does this happen? Give me median, high, and low. And we put that in the models. And then we run what's called sensitivity analysis. So we say, hey, if we're off by 20% on this parameter or by 50%, does it affect the outcome? Because sometimes you can have a parameter where you're like, oh, I really want to get this number right because I think it's important. But when you run in your model, you're like, you know what? It actually doesn't matter for the outcome. Whether these organisms grow this fast or this slow, because growth rate is not a determining factor. It's not a major factor. So the models, it's an iterative process. The initial models will help us run sensitivity analysis, will help us direct us where we need more data and better data to make the models better. So at that level, we definitely provide that. I think one of our roles is really, at this point, where we are right now, to build the building blocks and put them out on GitHub and in publicly accessible formats where people can grab these building blocks and build some of these things, these digital twins, and you know, with a digital twin, it always depends on also how big you define it. It can't just be a processing plant. I'm pretty sure some food processors are already building those. often not for the type of work we described here today, but to optimize production efficiency, employee flow, etc. So those are some of the initial thoughts. But yeah, building a guidance in terms of how to get data and how to get to these digital twins is part of it. But the big part right now is really building those building blocks and making them available. Renata, you want to jump in?
Yeah, you explained everything that I would say. That was great. The only thing I'm not sure if it addressed the question about benchmarking. Maybe, or did it?
I don't know, you want to specify what you mean with benchmarking? I was thinking sort of like, what's good enough data that the model, either that you can build a model, or what's good enough data, or what's a good enough model will be the benchmark. Your model or your data have to fulfill X, Y requirement, which I think will be very difficult to sort of come up with a generic benchmark.
I guess the benchmarking that I had in mind is more that most companies are collecting data on a regular basis, right? And like you say, giving them some guidance as to what data might be useful with a model. They have benchmarks. They make benchmarks for all kinds of purposes. And so then the question is, what things do they need to do in order to have a good sensitivity analysis? Because they don't necessarily have to do a model today, but they do benchmarks all the time. And so the question is, from an industry standpoint, you're working with the IDFA, does it make sense to think a little bit about what kind of guidance or advice you can give the industry even before they've determined that they have to build models, but to begin to set these things in motion so that when these models are better made, or not better made, but when you have more models or when you have more experience with them, they're positioned to start using them.
But thank you, that explained. And it goes back, I think, to what Martin was saying. The process is iterative, and what I think needs to happen, communication with industry, so that if the model identified that out of 10 parameters or inputs in the model, only 2 are very important, key to the dynamics, then we go back to the industry and say, for those 2, we really need more data. And then if there is prospect, the industry feels that, yes, the model could be useful, then the industry may be responding with more data in that area, whether it's shared with us or the industry is using the model by themselves as an internal tool.
Yeah, to add to thing, you poke in the proverbial bear here a little bit, because it's a part is a huge issue that we ran more into with some food safety data, and I'm gonna illustrate and might exaggerate a little bit, but we could get data saying, oh, our water 20% is salmonella positive, build us a model with it, and then we go back to, well, what volume you testing? They're like, yeah, we don't remember that. We didn't write that down. I think, for the 2018 data, maybe it was 25 mils, but we're not sure. So the data standardization, which is I wouldn't call it benchmarking, but I think it's part of it, is like, how do you capture the right data and enough information that the data are useful? Because we do see this issue that we get industry data, and it can range from the very simple, like no denominator, we don't know what volume you tested, to the more challenging one that there's just simply not enough metadata. And we've just have through a completely different, more sort of food safety projects, trying to come up with some, I'm going to call it data standards, and Renata will correct me if that's not the right term, for some of the food safety data. They say, industry, hey, if you collect water testing data, here are really the data standards you should have, so to make the data useful that we can do modeling. So I think that's a whole other thing. We have not really focused much on that on the spoilage area, but it's going to be an issue, absolutely.
This is Sarah Murphy. I'm just going to add to what both Renata and Martin have been saying. We actually, Phyllis, ran into this with one of our not yet published projects involving the spore model, where we asked a company for data and we actually couldn't use it because they weren't using methods that were robust enough in terms of our ability to use that as a validation data set. So you're definitely right about protocols being important. And so if anybody is actually interested in using our models, we do, and in every publication we have, we describe the methods that are used to collect the data sets, or at least we cite the data sets, which are linked to papers where then there's the methods are described there on how those data are collected. So it is there, but it's not totally, there's not an official protocol yet.
Right, and I guess that's what I was saying, is that to the extent as you publish these things, you can devote some information to what's really important and what sensitivity analysis showed was important about how you collect the data. I mean, you look at, those of you who are familiar with Legionella data, if you don't do first flush, then it's not the same as everybody else has done first flush, and so it's not real useful. And one of the things that they found in developing standards for Legionella is that everybody does it a little bit differently. And so as you create these models, you said, let's make suggestions for what you can do. And so that's my suggestion. And that is to devote some specific information in your methodology as to what pieces, what turned out to be important about how you collected the data and what was really useful and what didn't really matter as much.
Yeah, I think that makes sense. And I think we're probably at a point where really specifically for fluid milk, we can and should make some of these recommendations. Yes, if you want to improve fluid milk shelf life and be able to test spoilage, here's some of the data you should collect, and here's how you should collect, and here's what information you should have. That's actually a really good idea. So thank you for that. Any other comments or questions? If not, we have the list of the people who signed up. So we'll send around a link to the slides and the link to the recorded presentation. If you have questions, feel free to contact any of us. If you have any suggestions coming down, or if you have some interest in collaborating, that would be great. Okay. I hear nothing else. Going once. Twice. Okay. Thank you all.
Thank you. Thank you.
Take care. Thank you.
Bye, Honor. Thanks, everyone.
Thank you.
Thank you.